As we continue to learn about forces and motion, the next topic we will be covering is projectiles. We'll start with a definition. The definition of a projectile is an object falling through space with only gravity as the force. If you think about dropping a ball off of a table, as the ball falls to the floor, the only force that acts on it is gravity. The same thing is true if you were to throw a baseball. When you throw a ball, you give the ball some force, but as soon as the contact between your hand and the ball is over, then the force is over. And what remains is the momentum that carries the ball through the air. So a projectile is an object falling through space or being thrown through space with only gravity acting as a force. Because a projectile still involves a force acting on an object, we can draw a free body diagram for any projectile. Let's take the first example of a ball rolling off a table. Here's our table. And the ball rolls off the table and falls to the floor. When it is in midair, the only force that acts on it is the downward force of gravity. We also use the example of a baseball being thrown through the air. If you throw a baseball, it has a path where the ball goes up and then comes back down. And in the middle of that path, the only force that acts on the ball is the downward force of gravity. In both of these cases, we are leaving out air resistance so that our pictures will be much simpler, and eventually when we get to the calculations, those will be simpler as well. So no air resistance. The only force that acts on a projectile is gravity. Let's make a note by the baseball picture that there is a force between the ball and your hand when those two things are in contact. But once the throw is over, once the ball leaves your hand, whatever force being applied by your hand is gone. The next thing we need to know about projectiles is that all projectiles have some horizontal velocity. This is the velocity that carries them in the outward direction, away from the table or away from your hand. A projectile gets its horizontal velocity from a force that sets it in motion. Maybe you push the ball off the table or you throw the baseball. But once the object leaves your hand, the force is over, and what keeps the object in motion is inertia. All projectiles also have vertical velocity. They are moving in the vertical direction as well as in the horizontal direction. This is because the acceleration due to gravity pulls the object down. Remember that the acceleration due to gravity is 9.8 meters per second squared. What we're going to do next is look at the two different examples that we talked about in a little bit more detail. The first one is the horizontally launched projectile. This would be the example that we talked about where you push a ball off the table. It rolls off the table and falls to the floor. As we describe how this projectile is moving, we will need to use some new symbols to talk about the projectile's motion, and we're going to match those symbols to the directions that you use on a graph. So the vertical direction, or the vertical axis, is the y-axis, and the horizontal direction, or the horizontal axis, is the x-axis. So as we describe the projectile's motion, keep in mind that x goes horizontal and y is vertical. The first thing that we can say about the motion of a horizontally launched projectile is that the velocity in the x direction is constant. This is the velocity that the projectile gained from whatever force set it in motion originally, and that velocity stays the same. It never changes. The next thing that we can describe about a projectile's motion is the velocity in the vertical direction or in the y direction. This direction is affected by gravity. So Vy, or velocity in the y direction, is gradually changing. That is because it's either accelerating or decelerating due to gravity. The third thing that we need to know about the motion of a projectile is that the vertical and horizontal parts to that motion are independent of each other. The velocity in the x direction and the velocity in the y direction do not depend on each other. They are independent, and that means we can treat them independently, so we can look at one at a time, and that simplifies things when we do our calculations. The Italian astronomer Galileo is credited with coming up with the equations that we use to describe the motion of a projectile. We have one equation that will work for the horizontal direction or the x direction, and three equations for the y direction. This first equation will be the one we will use for velocity in the x direction or in the horizontal direction. And this equation says distance in the x direction is equal to velocity in the x direction times time. We can also put this into our algebra triangle. D is in the top, Vx and t are on the bottom. The next three equations get used for the vertical direction or the y direction. So these three equations are used to describe the motion in the up and down direction. The first one is used to solve for time. If you need to know how long the projectile is in the air, time is equal to the square root of 2 times the height, that would be how far it's falling, divided by the acceleration due to gravity. This third equation will actually be a rearrangement of the second equation. So equations B and C are exactly the same, they're just solved for different letters. The next version of the same equation from B is solved for height. So if you need to know how far the projectile is falling, height is equal to 1/2 times the acceleration due to gravity times time squared. This last equation for the vertical direction has to do with the object's velocity. Velocity in the y direction is equal to the acceleration due to gravity times time. Note that the three equations in blue are all for the vertical direction, and the one in green was for the horizontal direction. And perhaps we should put a couple of other notes. Maybe you could put these off to the side. Note that time should be in seconds. Velocity will be in meters per second. Distance or height will both be in meters, and the acceleration due to gravity is always 9.8 meters per second squared. The next thing we're going to do is create a diagram or a picture of all of the things that we just talked about in our equations. So this picture shows a projectile being launched horizontally off a cliff. You can see that there are two different paths pictured here. This one at the top is called the inertial or the gravity-free path. If there was no gravity, the cannonball would go straight out from the cannon and keep going. But we know that there is gravity, and so the cannonball actually follows the projectile's path. As it travels outward away from the cannon, gravity pulls it down to the ground. Now let's see what we can label on here. We talked about finding the height that the projectile was falling, so we can label the height. Remember, that would be in meters. We also talked about measuring or calculating how far the projectile would go, and that would be the distance that it travels away from the launch point. Sometimes this goes by another name. Sometimes this is called range, which should make sense if you think about describing the range of a rifle, for example. The next thing we'll put on here is the velocity in the horizontal direction. And remember that the velocity in the horizontal direction remains constant throughout the flight of the projectile. So we can draw an arrow to symbolize the velocity in the x direction. And because that velocity remains constant throughout the flight of the projectile, at any point along the path, that velocity in the x direction would be the same at any point in the path until right before it hits. So perhaps we should make a note, and we'll see if we can put it right up here. Vx is always the same. That means when you draw the arrow to represent the velocity, it's always the same length because the velocity in the x direction is constant throughout the path of the projectile. Next, let's put the velocity in the y direction on our picture. Right at the split second where the cannonball comes out of the cannon, before it's had a chance to fall, the velocity in the y direction is 0. And that's right there. Right there, the velocity in the y direction is equal to 0. It hasn't started to fall yet. Gravity has not started to act on it yet. And so right at that split second, velocity in the y direction is 0. But as the projectile falls, gravity will make it accelerate towards the ground. So as the projectile goes through its path, the velocity in the y direction is increasing. So we make our arrows get longer as we go through the path of the projectile. And this last one here is supposed to represent the projectile just before it hits the ground. The split second before it hits the ground is where it has the most vertical velocity. So let's put a note for that out to the side as well. Vy gets bigger, or faster you could say, as it falls because of gravity. Gravity makes it accelerate in the downward direction. Now let's look at some examples of a horizontal launch projectile. Suppose a rescue plane drops a relief package while it's moving at constant horizontal speed at an elevated height. Assuming air resistance is negligible, which means we're going to ignore it, where will the relief package land relative to the plane? Your choices are below the plane and behind it, directly below the plane, or below the plane and ahead of it. If there's no air resistance, that means that as the projectile falls, the vertical movement is separate from the horizontal movement. So once the plane has let go of the package, the only force that it has is gravity. So when you look at where the package is going to land, at A, at B, or at C, it turns out that the package lands at B, directly below the plane. This is because the horizontal motion and the vertical motion are separate from each other. So the horizontal motion of the plane doesn't affect the vertical motion of the package. Example number 2. A cannonball is launched with a horizontal velocity of 125 meters per second off the edge of a cliff. It takes 25 seconds for the cannonball to hit the ground. The first part of this example says draw the situation to the right with the vertical and horizontal components. That means we need to put in the arrows that represent the vertical and horizontal velocities. Remember that the velocity in the horizontal direction always remains constant throughout the flight of the projectile. So as you put in your horizontal velocity, each arrow should be the same length because the horizontal velocity remains constant throughout the entire flight of the projectile. And we should label that Vx. Then, as you put in your vertical velocity, at the very first spot, the vertical velocity is 0 because gravity has not yet begun to accelerate the cannonball. And then, as you draw your arrows, they should get longer as the projectile falls because the acceleration due to gravity is making the projectile fall faster. Part B for this example says, how high is the cliff? So we need to find the height that our projectile fell. So this means we need to solve for h, and that will come out in meters. The equation that we had that solves for h says height equals 1/2 times the acceleration due to gravity times the times squared. So when we solve for h, we have 1/2 times 9.8 times 25 seconds squared. So the height of this cliff turns out to be 3,062.5 meters. Part C says, what is the range of the projectile? Remember that range is the same as finding horizontal distance. So for this part of the example, we will need to solve for d. And this will still come out in meters. The equation that we had to solve for distance is distance equals the velocity in the x direction times time. You could also use your algebra triangle for this. We're looking for distance So we would cover that distance, cover the distance, and what you have left is velocity times time. So that's what we need to do. Velocity times time. Plug in the numbers. Distance is equal to 125 meters per second times 25 seconds. So the horizontal distance turns out to be 3,125 meters. Here's example 3 for a horizontal launch. A student threw a ball horizontally out of a window 8 meters above the ground. It was caught by another student who was 10 meters away. What is the initial horizontal velocity with which the student threw the ball? Hint: find time first. When I start to do a projectile problem, I usually like to begin by drawing a picture and labeling the things that I know and the things that I'm looking for. I know that I have a building with a window that is 8 meters above the ground. I know that there is another student outside the window ten meters away. I know that there is a ball getting thrown out the window, and the student, who is 10 meters away, is going to catch it. I'm looking for, eventually, the initial horizontal velocity that the ball had when it exited the window. And my hint says that I should find time first. So let's find time first. The equation that we know to solve for time says time equals the square root of 2 times the height divided by the acceleration due to gravity. Our height was 8. The acceleration due to gravity is always 9.8. And so to put that in your calculator, you're going to have to do the stuff inside first. So that becomes 16 divided by 9.8. This gives you the square root of approximately 1.63, which equals 1.28 seconds. Now that we know time, we can solve for the initial velocity. The equation that we had with initial velocity in it was the one that came from our triangle, where distance was on the top, velocity and time were at the bottom. So if we cover the velocity, because that's what we're looking for, what's left is distance divided by time. So that's what we need to do. The velocity in the horizontal direction is equal to the distance divided by the time. Our distance was 10 meters divided by the time, 1.28 seconds, and that gives us an initial velocity of 7.8 meters per second. The last thing we're going to look at today are projectiles launched at an angle. For example, like in the picture, if you throw a ball up and out, and then it comes back down. There are 3 things that are true about projectiles launched at an angle. The first one is the same as for a horizontal launch. The the velocity in the x direction is constant. It stays the same throughout the path of the projectile. The second thing that's true about projectiles launched at an angle is that the vertical velocity decreases on the way up and increases on the way down. This is because gravity is always pulling down. And so as you try to throw a ball up, gravity pulls down and slows the ball on the way up to the top of the path. Then as the ball turns around and starts to come back down, gravity makes it go faster. So Vy decreases on the way up and increases on the way down, both because of gravity. The third thing that's true about projectiles launched at an angle, the same as for a horizontal launch, is that Vx and Vy are independent. The vertical motion is independent of the horizontal motion. There is one more thing that we'll add to our list, and that is a note about which angles produce the greatest range. Remember that range is the distance in the horizontal direction. So which angles of launch would produce the farthest distance away? You might be able to guess that the angle that produces the furthest range is 45 degrees. This will give you the largest possible horizontal distance. One other thing that's worth noting, however, is that corresponding angles, for example, 30 degrees and 60 degrees, both of those two add up to 90, would produce the same range. And so your projectile would land in the same spot if you fire at 30 versus if you fire at 60 degrees. We're going to do one last thing, and that is to sketch a picture at the bottom of your page of what the arrows would look like for this angled launch. In other words, what would the velocities be for this angled launch? Perhaps we're going to have a cannon launch a cannonball at an angle, and that cannonball will go up and then come back down. Let's label what we know. The horizontal distance is called the range. The height is now in the middle of the projectile's path. And the time could be either the total time for the whole flight, or you can sometimes describe the time to the peak or to the top of the path. Next, we'll pick some spots to look at the velocity for. Right here at the beginning, about halfway up, at the top, about halfway down, and then pretty close to the end. We're going to draw the velocity arrows for these 5 places in the path. Let's put the horizontal velocity on here first. We know that the velocity in the x direction remains constant throughout the path of the projectile. So each of our points gets an arrow to represent horizontal velocity, and they should all be about the same length. Next, we'll put on the arrows for Vy, velocity in the vertical direction. If you think about it, it should make sense that at the beginning of the path, the velocity in the vertical direction going up is the greatest. And as the projectile rises, that velocity slows and your arrow gets smaller until at the very top, that split second before it starts to come down, Vy equals 0. Then on the downside, Vy starts off small and gets larger because the projectile is being accelerated by gravity. One last note to make. If you know about parabolas from math class, you know that that's what this shape is. And you also know that parabolas are symmetrical. Because they're symmetrical, corresponding opposite locations on the path have equal and opposite velocities in the vertical direction. For example, if you took the second point and the fourth point, those velocities would be the same. Maybe it's 5 meters per second up and 5 meters per second down. It's the same amount, but in opposite directions. And that's it. Now we're done with our projectile notes.